Well, this video is Chapter 2, Section 3, dealing with polynomial functions of higher degree with modeling. What you're going to learn about, we're going to learn about graphs of polynomial functions, end behavior of polynomial functions, zeros of polynomial functions, the intermediate value theorem, and modeling. And why are we going to learn this is because these topics are important in modeling and can be used to provide approximations to more complicated functions, as you will see if you study calculus. So the vocabulary of polynomials: each monomial in the sum a sub n x to the n, comma, a sub n minus 1 x to the n minus 1, comma, and so on until a sub 0 is what we call a term of the polynomial. A polynomial function written in this way, with terms in descending degree, is written in what we call standard form. The constants a sub n minus 1, and so on until a sub 0 are what we call the coefficients of the polynomial. The term a sub n x to the n is the leading term, and a sub 0 is the constant term. And what's going to happen is you'll find that a sub 0 is a y-intercept of our graph of our polynomial function. So describe how to transform the graph of an appropriate monomial function f of x equals a sub n x to the n into the graph of h of x equals negative quantity x minus 2 to the fourth plus 5. Sketch h of x and compute the y-intercept. So how do we take this general function f of x equals, in this case, x to the fourth? This would be the parent function. What all happens to that graph to obtain h of x equals negative quantity x minus 2 to the fourth plus 5? So there's some interesting things that happen to the parent function here. We have this negative sign in front of our quantity. We're subtracting 2 inside the quantity from x, and then outside the quantity here we're adding 5. So those are three things that are going to do something to the graph of the parent function x to the fourth. And we need to know what each one of those is. So words like translation, reflection, compression, or stretch, these particular values are going to do those types of things to our graph. So we can obtain h of x equals negative quantity x minus 2 to the fourth power plus 5 by shifting the graph of f of x equals negative x to the fourth 2 units to the right and 5 units up. The y-intercept of h of x is negative 11. You can see why here. So we didn't really talk about the negative coefficient on x to the fourth, but really the parent function is x to the fourth. So the graph of that parent function would look something like this. In general, come down, go back out like this. So the first thing that we have that was assumed is to get the blue curve from the green curve is we have a reflection across the x-axis because of this negative value here. And then we get our various translations. So in general, here on the left here, we have two graphs of some cubic functions. Okay, so again, we discussed cubic functions in our last lesson. We need to know the general nature and behavior of a cubic function. We have ones that go from down to up, and then over here on the right we have some that go from up to down, and we need to discuss their end behavior, not only in those terms but in also terms of limits. Here we have quartic functions. Again, quartic functions have the behavior of an up-up scenario, up-up here on these two on the left, and we have down-down in those two on the right. But again, up-up, down-down is not the proper technical terminology that we need to use. We need to discuss the end behavior in terms of limits. The local extrema and zeros of polynomial functions. A polynomial function of degree n has at most n minus 1 local extrema and at most n zeros. So what that means is that a third degree, let's say x cubed, some type of a cubic function could look like this. And what this says is that that curve can have at most 2 extrema. which kind of makes sense. If I put the x-axis on here, we can see that this curve can hit the x-axis at most 3 times, having 3 zeros. So the power of the function tells us at most how many distinct zeros there are, and it tells us at most how many extrema there are. And again, the key is at most. For any polynomial function f of x equals a sub n, x to the n, and so on, the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x are determined by the degree n of the polynomial and its leading coefficient a sub n. So here we have our odd function graphs. If a sub n is positive and n is odd, then this is the general behavior. As x goes to negative infinity, our limit of our function is negative infinity. Okay, the graph goes downward to negative infinity. As x increases, as x goes to positive infinity, the limit of our function is positive infinity, meaning the values of the function increase without bound. And if a sub n is negative, and n is odd function, leading coefficient negative, as x goes to negative infinity, so as we travel out this way on the x-axis, the curve is going upward, so its limit is positive infinity. Okay, so those values of the function increase without bound as x gets infinitely small. And as x goes to positive infinity, the limit of our function is negative infinity. So the values of the function decrease without bound as x gets infinitely large. Here we have an example, or 2 examples of where even functions. So if our leading coefficient is positive, here on the left, this is what the graph would look like, and here you have our limits. Okay, as x goes to negative infinity and positive infinity, those 2 limits are equivalent. And when n is even and the leading coefficient is negative, here we have equivalent limits. As x goes to negative infinity and positive infinity, the values of the function are negative. So describe the end behavior of g of x using limits. G of x is 2x to the 4th minus 3x cubed plus x minus 1. So what would the end behavior of that function be? If you want to pause the video for a second, think about that and write it down, and then play again, I will give you the solution. So the limit of g of x as x goes to positive or negative infinity is going to be infinity because g of x is an even function. It's an even function with a positive leading coefficient. So in general, its graph is going to look something like this. Okay, and that's not what the graph looks like, but in general it's going to look something like that. Okay, could have 3 extrema, and if I put an axis on here, it could have 4 zeros, 4 distinct zeros. Find the zeros of f of x equals 2x cubed minus 4x squared minus 6x. So find zeros, and when we find zeros, unless we're told specifically to use our calculator to do it, we are going to do this what's called analytically. Analytically means algebraically, meaning we're going to do it by hand. And we should be able to do this. So pause the video, find the zeros, and then when you're ready, play the video again. So when we solve for f of x equals 0, that's what we have to do, set the function equal to 0. So here's our function equals 0. We factor, first step is to factor out the GCF of 2x, which will leave a quadratic that we can factor into 2 binomials, which gives us these 3 zeros. If f is a polynomial function and the quantity x minus some c to the m power is a factor of f, but the quantity x minus c to the m plus 1 power is not, then c is a 0 of multiplicity m of f. So this is a multiplicity property of zeros. If a polynomial function f has real 0 c of odd multiplicity, then the graph of f crosses the x-axis at c, 0, and the value of f changes sign at x equals c. If a polynomial function f has a real 0 c of even multiplicity, then the graph of f does not cross the x-axis at c, 0, and the value of f does not change sign at x equals c. So basically what this is saying is that if a function has a real zero of odd multiplicity, then the graph is going to cross the x-axis at that zero. And if the function has a real zero c of an even multiplicity, then the graph is not going to cross the x-axis. It's going to touch the x-axis and head back the other direction because the function does not change value. So using that information, sketch the graph of f of x equals the quantity x plus 2 cubed times the quantity x minus 1 squared. Now, we can't really do this one by hand, but we should be able to discuss some of the characteristics of the graph. So you can use your technology to graph this if you'd like, but if I ask you to discuss the behavior of the function around its zeros, this function has two zeros, -2 and 1. The 0, -2 has a multiplicity of 3. So we should be able to do some analysis on that 0. What happens to the graph around that 0? The 0 and 1 has a multiplicity of 2. So again, we should be able to discuss the graph and the behavior of the graph around that 0. So again, the zeros are x equals -2 and x equals 1. The graph crosses the x-axis at x equals -2 because the multiplicity 3 is odd. The graph does not cross the x-axis at x equals 1 because the multiplicity 2 is even. So this is what the actual graph of this function looks like. So questions that you should be able to answer are the end behavior and the behavior of the function around its zeros. We haven't really talked about how to determine extrema, like this point right here. We will have some techniques later that we can use to determine those extrema. All right, so we come across this interesting theorem, and it seems very basic, but it's a very powerful theorem. And it's a theorem that a lot of what we do in calculus will use this theorem, and this theorem will be kind of a standard or an assumption of truth in order for other theorems to evolve from it, and it's called the intermediate value theorem. Here's what the intermediate value theorem says. If a and b are real numbers with a less than b, and if f is continuous on the interval a to b, then f takes on every value between f of a and f of b, meaning the function has every value between the value of the function at a and the value of the function at b. In other words, if some y value, y sub 0, is between f of a and f of b, then y sub 0 equals f of some value c for some number c in the interval a to b. In particular, if f of a and f of b have opposite signs, i.e. one is negative and the other is positive, then f of c equals 0 for some number c in the interval ab. And I'm going to show you what this means graphically here in just a second, but if you think about that last statement, here's the power of the intermediate value theorem. If f of a were to be positive, and f of b were to be negative in this case, that means the function changes sign somewhere in the interval a to b. And in order for a sign change to occur in the value of the function has to assume the value of 0. So we can narrow down where zeros are for a function if we observe the behavior of that function. Here's what that would look like graphically. So here we have our x value of a. Okay, here's the x-axis. And here we have our x value of b. A is less than b. And here we have some function, some blue curve. And at this point right here, we have a, comma, f of a are the coordinates. And up here, we have b, comma, f of b for its coordinates. So if this is the x-axis, here at this function value, f of a is negative, less than 0. And up here, at this value, f of b is greater than 0. So somewhere in this interval from a to b, the function takes on the value of 0, and it occurs at this value c, some value c. Okay, the intermediate value theorem says we don't know what c is, but we do know that there exists a c somewhere in this interval where f of c is 0, based on the intermediate value theorem. Pretty cool theorem. Okay, so here's some quick review problems dealing with the lesson. So at this point I would pause the video, I would work these problems out in my notes, and when you're ready, I would unpause the video, I will show you the solutions. Anything that you miss, along with any other questions that you have on the video, please be prepared to ask those in class. Alright, so hopefully you did well on those. If not, we can talk in class, and have a good day, folks.